Hello everyone. Welcome to my presentation on the multi-step framework for training physics-informed neural networks. I am Agnimitra Dasgupta and I'm a student at the Soni Astani Department of Civil and Environmental Engineering at USC. This following presentation was presented as part of the Deep Learning Symposia organized by the Department of Electrical and Computer Engineering in USC. Today I'll be covering some topics which include an introduction to the universal approximation theorem for what physics-informed neural networks are, a multi-fidelity physics-informed neural network that has been recently proposed, and I will introduce that and include some numerical experiments on that, and finally I'll be discussing reliability estimation, which chiefly includes estimation of failure probability, a domain adaptation technique for training the multi-fidelity physics-informed neural networks, and some numerical experiments. And I'll end with a summary. You can consider any model which maps from its input to output space as, for example, it can be a differential equation. For example, it can be a simple function which maps any variable x to y. Now, you can conceive of this model as being a map from its input to output space. Take, for example, the heat equation. U dot equals to grad square u, where u dot is the partial derivative of u with respect to time, and grad square is the Laplacian operator. Simply, in one-dimensional, the heat equation is a map from x, t, which is at any given point of space, and at any given instant of time, L maps from that to u, which is the solution. Therefore, the universal approximation theorem dictates that under certain conditions, smoothness conditions and other criterias, the universal approximation theorem dictates that L can be substituted with a neural network. But this raises more questions than answers. How much data do we need to approximate L with a neural network? And how complex should the network be? Let's take an example for simple function, a simple trigonometric function which is essentially nonlinear. If we try to fit a neural network by just selecting very few number of training points, indicated here by the blue dots, then you will see that a simple task in regression is not sufficient to approximate y with a neural network. Now, you could always improve this accuracy by including more training points or making the network more deep. Unfortunately, for many tasks, our computational resources are constrained. We cannot indefinitely increase the number of training points, nor can we indefinitely make our neural network model more complex. Now, recently it was proposed that the loss function be augmented with an additional term here. Now, this term not only forces or sort of trains the neural network to match y at every training point, but also the gradient of y with respect to x. Now you will see that what this does is essentially constrain the optimization problem. So this term essentially acts like a regularizer to the problem, to the neural network in hand. And you can immediately see an improvement in our predictions using neural networks. Now, this is implemented for a very, very simple neural network which had 4 hidden layers and 20 neurons with hyperbolic tangent activations. And it was trained for over 50,000 epochs on very few training points. Even with that, we can see that this approach works very well. And this sort of gives a very gentle and nice introduction to what physics-informed neural networks are. Now, let's dive in deeper. Consider the one-dimensional Burgers equation. Okay, it's ubiquitous in the domains of fluid mechanics. Maybe some of you would have seen it in your first your partial differential equations. It's essentially an initial boundary value problem. There is an initial condition which must be satisfied, and there are boundary conditions which must be satisfied. Now, this problem was extensively studied in a paper which the first author of which was Professor Mazia Rassi from Brown University. This problem is essentially adapted from that paper. The codes are also available in GitHub. So, now, this governing equation of the Burgers equation actually gives us an augmented mean squared function, error for a loss function. Now, see, any solution that the neural network proposes must approximate or must satisfy this equation to the best extent possible. So we add that term additionally along with the initial and boundary conditions that must be satisfied by the neural network. Together, the loss function is a simple mean square error loss function, but it's augmented. So it's slightly different. It's informed for the physics. And these quantities, u dot and grad u, are computed using automatic differentiation, which is very, very common in the domain of neural networks. Now, and this is a result represented from the paper which introduced this problem. And as you can see, that the physics-informed neural network works very well in approximating the differential equation in hand, which in this case is the Burgers equation. In fact, the authors reported an L2 error of the order of 10 to the power minus 4, which is very, very impressive. Now, unfortunately, these physics-informed neural networks still require a lot of high-fidelity data. Sometimes these models from which data is obtained to train a physics-informed neural network might be very expensive to evaluate. Now, so we ask the question, or we propose the question, that can we reduce the amount of high-fidelity training data necessary to train physics-informed neural networks? To this end, another paper from the research group of Professor Kaniadakis at Brown University proposed a multi-fidelity physics-informed neural network, or a multi-composite neural network, which can be trained using multi-fidelity data. It consists of 4 essential parts. The first part, an NNL, which approximates the low-fidelity data, and an NNH1 and an NNH2, which together can learn the correlation between the low-fidelity data YL and the high-fidelity data YH. This part of the neural network is induced by the PDE that you're trying to approximate. NNL is first trained using the lower fidelity data. NNHI is used to capture the relation between high fidelity and low fidelity data. And NNH1, as I said, captures the linear relationship, therefore only has linear activations. Now, let's go back to our initial example. Right. So let's see what would happen if you had only 4 training points, denoted here by green, to fit a neural network. With no modified activation functions, it's not physics informed, you see that the neural network does a very bad job, and it's kind of expected. But if you have a low fidelity model, in which we're presuming that the data available from it is not accurate, as you can see, it does not predict YH very well, but can be obtained very easily, so we can have more training points over there, we can see that the neural network NNL can approximate this low fidelity model very well. And using that approximation, we can learn the correlation between NNL and NNH, which is YL and YH, to predict the actual output. Now, in this case, the correlation is linear. It could be nonlinear, as we have in this example. The same philosophy as before. However, you would see here that the low fidelity model actually presents with adversarial data to the high fidelity model, in that it's actually opposite in sign to what the high fidelity model would have predicted. Even in this case, we see that the multi-step physics-informed neural network proposed by Professor Kaniadakis and students works very well in capturing the response. Now, let's look at another example involving a jump function. Now, in this case, there is a jump, and jump nonlinearities are very hard to model. So we try to fit a neural network. Now, we reduce the influence of the gradients by using this gamma parameter in the original loss function. You will see that the neural network does not do a very good job in this case. All right? And this may be because the lower fidelity model actually does not do a very good job, given in this context. Now, there is a saving grace, okay? So let's look at a summary. We can augment the training set for physics-informed neural networks with low fidelity data and train these multi-fidelity physics-informed neural networks, which can capture the correlation between high fidelity and low fidelity data. However, the overall quality of the prediction depends on the quality of the lower dimensional, the low fidelity neural network. Okay? Now, let's take a step back. Let's look at the problem of reliability estimation. So given any model, L, which has uncertain parameters theta, the probability of failure is the area under the probability density function of theta for which f is evaluated to be greater to 0. This integral is often very hard to evaluate analytically, so we use statistical approximation techniques like Monte Carlo simulations. Now, the Monte Carlo estimate of a failure probability has a variance which is inversely proportional to your sample size. So, but directly proportional to your failure probability. What this means is that as the failure probability that you're trying to estimate gets lower and lower, you will need more and more samples to lower the variance of p hat of f. Okay? Now, say for example, you want to estimate a failure probability less than 10 to the power minus 9. So for that, you would need around 10 to the power 11 samples. And evaluating very expensive computational models these many number of times is simply not computationally tractable. To this end, we revisit the previous example of jump functions, where we define failure to happen when the high fidelity response exceeds a value of 17. Right. And we see that in the previous case, we would not have been able to accurately predict the failure probability using our models. However, there is a saving grace. We do not need the high fidelity neural networks or the physics informed neural networks to work very good over the entire domain. We just need them to work very good only near the failure domain, near the failure surface. So we can use the neural network, the lower fidelity neural network, to indicate where failure might happen. And using that information, we can then sample points uniformly near the failure surface. This can be easily done by lowering the failure surface to a certain amount. However, how much you should lower this failure surface by is often chosen using a hyperparameter that's chosen using optimization or cross-validation and other techniques. And you can do that. And doing that will allow you to predict the failure probability very, very accurately. The details of this approach are included in my report, and interested readers or people interested in this method are requested to contact me, and I would be able to share a copy of my report with you. Finally, I would like to summarize my talk by saying that physics-informed neural networks are very, very good at approximating physical processes, and therefore offer promise in reducing computational costs in reliability estimation tasks. More specifically, these physics-informed neural networks can be trained using multi-fidelity data, and therefore can be used in a small data regime. And more thirdly, the proposed domain adaptive training methodology can be used to improve the performance of the MPINNs, as I've already shown, for reliability estimation tasks. These are the references to my talk. Most of my presentation has been taken from the first 3 references, as you will find. And I would sincerely like to thank Professor Keith Chugg, who has been my mentor through this project. And I would also like to thank the support of NSF and the USC Provost Fellowship. But however, the views that I have expressed here do not necessarily mean the views of NSF or USC for that matter. Thank you.